Hey, physical science, it's Wednesday, April 8th, and we're going to do pages 465 to 468. I'd like for you to start with me on page 467, and I'm going to summarize what we learned last time. What we learned was about pure substances. We learned that matter is anything that has mass and volume. Anything that has mass and takes up space. That's the definition. Matter can either be pure substances, which can be divided into elements or compounds. An example of an element might be gold, silver, oxygen, and that kind of thing. Elements. It's on this table called the periodic table of elements. Then compounds are made up of elements like table salt, sodium chloride. And another might be, let's just say, magnesium oxide. You can see that elements go into making up compounds. And the way these are held together, they're held together chemically. So in order to pull them apart, you have to pull them apart chemically as well. I have over here that I'll show you on our next go around. I have a an electrolysis apparatus. See if I can let you see that. There it is, right there. In there, and I break H2O into its constituent elements, hydrogen and oxygen. I'll do that for the next lesson when we talk about chemical changes. But because these are chemically hooked together, they got to be chemically separated if you want to do that. Now, today we're talking about the other part of matter, which is called mixtures. So all matter is either substances, pure substances, or mixtures. Now, mixtures can either be homogeneous or they can be heterogeneous. Okay, and if they're homogeneous, they're called solutions. If they're wet, and alloys if they're solutions of metals. Now, homogeneous mixture might be something like sugar water. And what can you think of when I say sugar water? They dissolve. So solutions are dissolved. They have a solvent that the solute goes into, but those are words that are in chemistry. We won't worry about those. But like the sugar would go into the water and it would get cut down so small, the grains would be cut down to little teeny particles called molecules. And there's spaces between the water molecules where the sugar molecules can fit in between. And so since they're the molecular size, we can't even see them in solution. It just looks like water, but the sugar is still in there. Now, heterogeneous mixtures are things like fog, milk, now fog and milk are a special category of heterogeneous mixture called colloid. And there's another category of heterogeneous mixtures called a suspension. Now, a suspension would be something like muddy water. Or orange juice. Orange juice that has pulp in it. Like the kind I like to drink. They tell me it's better for me, so I drink it. Okay, homo means alike. And hetero means different. What does that mean? Well, let's go ahead and do some mixtures. Let's start on page 467. See where it says homogeneous mixture? Well, a homogeneous mixture is a mixture that remains constantly and uniformly mixed and has particles that are so small they cannot be seen with a microscope. And so the particles interact with each other and they remain intact in the solution. They don't settle to the bottom. You don't have to shake them up. They stay dissolved. And a solution is the same thing as a homogeneous mixture. And the reason we call it homogeneous, let's take a look at one. Here's salt water. Okay, here's my water. Here's my salt. Get the water going first. Salt in next. See it sprinkling in there? Pretty neat, huh? And if I get my stirring rod here, the salt goes away because it has dissolved. The water broke down the salt into teeny tiny particles and tucked them in between the water molecules. And you cannot see it, even with a microscope. Those particles are so small. They're smaller than 1 nanometer. It's a really small piece. Okay, that's it for solutions right there. Now, I'm going to give you another solution. You think that's a solution? What do you think's in there? Well, you've got, if it's a real ginger ale, not a diet one, you got sugar, tons of sugar, big old wad of sugar that's dissolved in there. Then you've got caffeine, if it's a Coke, that kind of thing. You've got some preservative, some, that's another type of powder. Caffeine would be a powder. And then you've got flavoring, and you've got carbon dioxide gas to give it the bubbling. And that's called carbonation. So that when you open it, you get effervescence because that carbon dioxide is dissolved in there under pressure. And when you release the pressure, it comes to the top. Homogeneous mixtures. Take a look at the picture on the top of 467. You cannot see a light going through a homogeneous mixture because the particles are so small, they don't scatter the light. But now let's go ahead and go left. Back over to 465. The heterogeneous mixtures, colloids and suspensions. All right, we'll start with what's the definition of a heterogeneous mixture? It's where different materials remain distinct. So I have this little picture here, and you don't have to have a water or anything to make a mixture. You can just start putting stuff in here. This is going to be a mixture of not projector pens, marker, white marker, dry erase markers. Okay, and what else we got in there? We got some rubber stoppers. And how about marbles and dropper poppers? That's a mixture. Now, are there dropper poppers everywhere in that mixture, or are they only over here? Do they have marking pens everywhere? No, they're only over here. Whereas with this mixture, is it salt water over here? How about over here? How about up here? How about down there? How about over there? It's salt water throughout. It's like it's diffused throughout the entire of the solvent. And so the salt is creating a uniform composition. It's creating a homogeneous mixture called a solution. This is a heterogeneous mixture because it is not everywhere the same. Plus, they said in heterogeneous mixtures in your book here that the different materials remain distinct. They did not chemically bond with one another. And so as a result, you can pull it apart. Now, this is a mixture of pens, rubber stoppers, dropper poppers, and marbles. Is this still a mixture of pens and dropper poppers? How about this? And pens and rock. Okay, those are still the same mixture, a mixture of pens, dropper poppers, rubber stoppers, and marbles. It doesn't matter how many pens you have. So in terms of mixtures, you can vary the composition. Varied composition, you still have the same mixture. But in the case of substances like compounds, it's a definite composition. Because water is always H2O1, 2 atoms of hydrogen with 1 atom of oxygen. Magnesium oxide is always MgO, 1 atom of magnesium with 1 atom of oxygen. Sodium chloride is always NaO, 1 atom of sodium with 1 atom of oxygen. And if you change that, it isn't water anymore. Let's take a look at that. H2O2, let's change it. It isn't water anymore, it's hydrogen peroxide. If you change this down here, make it Mg2O1, you have something that doesn't even hook together. It doesn't exist. Okay, so while substances have definite composition, both elements and compounds, mixtures have a varied composition, and they're still called the same mixture, a mixture of pens, dropper poppers, marbles, and rubber stoppers. Okay, now, would this still be a homogeneous mixture? Would it still be a mixture if I added more salt? Yeah, whether you have a little salt or a lot of salt in that same amount of water, it's still a mixture of salt water. So it can have a varied composition. That's my point. All right, so in a heterogeneous mixture, it is not the same everywhere within the mixture. But in a homogeneous mixture, it is the same everywhere. I'll pick up there tomorrow. We'll talk about a little bit more about the difference between colloids and suspensions, and I'll show you the Tyndall effect tomorrow.